This video proposes a classical alternative to Planck scale cosmology. We suggest a reformulation of the cosmos's origin using classical electromagnetic and thermodynamic principles, avoiding the need for quantum singularities. Standard cosmological models assume initial conditions where classical physics breaks down. This relies on physically inaccessible parameters at time equals 0, creating a discontinuity. This is linked to the physically ambiguous extreme energy density and the vanishingly small volume at the Planck scale, leading to the concept of a singularity. We challenge the necessity of a singularity. Our hypothesis suggests the initial state was a coherent, light-dominated configuration, a transition from a broken point of math to an organized photon gas or concentrated beam. To address the problem of undefined mass at the start of the universe, we reformulate Einstein's famous equation. By substituting mass with density and volume, we define energy using parameters that remain physically meaningful in a radiation-dominated epoch. Assuming spherical symmetry and a causal horizon expanding at the speed of light, volume becomes a function of cosmic time. This allows us to define the combined energy equation as time-dependent. The speed of light arises from the vacuum properties of space, as defined by vacuum permittivity and permeability. Substituting this into our energy definition connects cosmic energy directly to vacuum polarization properties, removing gravitational constants. The master formula for cosmological energy expresses a universe driven by classical electromagnetic parameters, independent of Planck units. It incorporates time-dependent density, volumetric expansion, and the electromagnetic vacuum factor. Modeling the early universe as blackbody radiation allows us to express energy density via temperature using the radiation constant. This results in a scaling law where energy scales with the fourth power of temperature and the third power of time. Quantizing the initial state links macro-scale expansion with microscale particle content. This formula calculates the precise number of photons in the expanding volume, grounded in thermodynamic quantization. For stability, radiation pressure must overcome gravity to prevent gravitational collapse. The universe must have been hot enough to sustain its own expansion against gravity, which provides a falsifiable constraint on the minimum temperature. If the universe originated as a directed pulse, or anisotropy, rather than an isotropic sphere, the geometry of the origin dictates a different scaling law for energy. Comparing the Planck scale and light origin models reveals key differences. The light origin model achieves a classically coherent status with manageable volume and calculable density, avoiding the quantum breakdown of the Planck model. The compactness parameter, chi, is a dimensionless ratio quantifying the proximity to a singularity. Our light origin model exists in the classical regime, while the Planck model approaches the singularity regime. The implications of a classical origin include no singularity, bridging the gap between classical field theory and cosmology, providing testable parameters, and predicting an initial mass equivalent of about 10 to the power of -2 kilogram. By reformulating mass-energy equivalents, we propose a universe that began not as a broken point of math, but as a coherent, luminous field. This framework offers a mathematically tractable path to understanding our origins, grounded in light.